Very good. I was studying, alternate yesterday and Sunday, doing UPD over. So much really, but they do much more. Yeah, those are two, three, five. It is fun. It's very profitable. Yeah, it's very down because they I think it might be interesting if I do this and maybe what I'm doing in mobile development.
Yeah, I would encourage that synergism between classes and topics and see how you can be helping that, but I'll get into that when we formally start. So,
Thank you for your input, so
yeah.
appreciate it. Like I know it's a lot, but I feel like that. But you know, personally, I feel the workload is. Finally, work this. I'm so glad I had my day off.
There's a outlet over there if you need it. Yeah. There's one here too if you want to string it in.
I thought it was better. It's just like up there, I guess.
Oh.
Thank you, President.
Hello. Okay, I'm gonna go ahead and get started out of respect for your time. I'll start on time each time we meet. So let me go ahead and open up in prayer and I'll give you a sense of what we're going to be covering today. So dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. I pray that the material will be clear, that it can be an enjoyable process as we get a better understanding of computer architectures. Pray that you'd be working in each of the students' lives as they're spending time here at APU, not only learning technical skills, but character development, understanding scripture. Pray that you would help them to really get a lot out of those time studying the Bible and the theological concepts that they can be pulling from that and be able to think of interesting and creative ways for spiritual formation here and things that they can be leveraging in the future, and have faith integration and various ways that you would open doors for them in the future. In Jesus' name we pray. Amen.
Amen.
So what I was hoping to do today was I'll first start with some lecture things here. And so I'm going to just briefly summarize a few more concepts in chapter 2 when we were talking about performance concepts, because there's things that we're going to be leveraging later on. And then I'll get into the top level view of computer function and interconnection. I was having some informal conversation with a couple of folks about your project work, and so I'll save some time for towards the end of our time together to get into that a little bit more in detail, to maybe give a perspective if you're still trying to figure out what you want to be doing on your project. It came up, well, I'm taking mobile app development, and maybe could I relate what I'm doing in this course with that? And of course, I would highly, that would be great. So feel free to do something like that. That would be a wonderful possibility. So like I said, I'm just going to cover a few more concepts in chapter 2. and then move on. What I found installing that there is a lot of really good information, and sometimes it can get a little bit complicated. And so that's good. So you can be thinking of this whole range of possibilities. I'm treating this more as a survey course that we're getting introduced to this, but also trying to get a little bit going into, give an analogy, maybe you've heard this, like you go into a restaurant and you sit down and you have a nice meal. That would be one way of experiencing what's going on. Another way of experiencing that meal is to go into the kitchen and see how they actually prepare it. And so we're getting a chance to do a little bit of both. We're getting a chance to sit down in the restaurant of computer architectures, but also go back into the kitchen and get some perspective on it. And so we were just starting to think about, well, how do we consider performance? And some of the basic ways of measuring performance is the clock speed. And so it used to be that one thing is how fast is the clock speed, used to be in megahertz, then gigahertz, and then going faster and faster. And eventually, as I was trying to allude to last week, you get to a point where the electronics and the density of things are so great that you can't go any further with that. Another way is looking at it is instruction execution rate, MIPS, instructions per second, or floating point operations per second, flops, megaflops. Those are the kind of things that are out there. And so we got a chance to be exposed to a couple of interesting principles here, and I'm going to defer to some of that for you to be looking over in the textbook. This is a figure that I showed you, was just trying to show the trends over time, things that were happening, that the density of transistors are getting higher and higher. I think in terms of microelectronics, the chips, I think the highest density, I think, is somewhere on the order of just a few nanometers. And so they're getting smaller and smaller in size, the size of transistors. And so thus they could pack more and more into a small area. But guess what? That means you're going to have more and more power in a small amount of area. And, if you just get it too high, it's just going to melt all of the components. And so those are some issues. The frequency is getting flat because it can't make it go faster, because once again, the faster you make it go, the more power that needs to be dissipated. And so the thing that has started to click up is going to multiple cores, and we'll get a chance to be thinking about that more and more in terms of what is the impact of when you start to add more cores. So this was a chart that I was looking at before class and was just annotating a little bit more. What are the performance factors and how are they related to system attributes? And so this is in the textbook table 2.1. And so you can feel free to look at it. And they're sort of like kind of like the instruction set and compiler technology seems to be more aligned to stuff that's going on with the instruction count, the number of processor cycles, and the number of memory references. And then over here, when we get into the processor implementation and cache and memory hierarchy, we get into these other things. Here is a ratio of memory time to processor cycle time and processing time. So there's just a lot of factors that are out there. So once again, just thinking back to the introductory slide for this chapter, how are we going to come up with a basic measure of computer performance? Well, these are kind of cool, but guess what? If I write a program one way, we're going to be doing a chance to be looking at assembly language, and say we both write it slightly different, and maybe mine is 10% less efficient than yours. That could make a huge impact if that's done a lot. And so thus the latter part of this chapter gets into benchmarking principles, and then it talks about this one specific way of doing benchmarking, the spec benchmarking. And so I'm just going to go forward to that and just spend a minute thinking about that. So here, there in the middle of this chapter, it gets into ways of comparing different ways of what is the average performance or mean, and they come up with a couple terms, arithmetic and harmonic means. I'm not going to get into that for for the sake of just trying to keep this at a high level for here. So what are the desirable characteristics of a benchmarking program? And is it written in a high level language, making it portable across different machines? So, since some of you have Macs, but actually it even applies to Windows. I know Windows now has an x86 architecture and an ARM architecture. You could have the same code, but then you have to compile it for a certain processor. And so thus we can be trying to figure out, well, what about this processor versus that? Does it actually perform better? And so you want to have something that's a high level language that is portable. It is representative of a particular kind of programming domain, such as system programming, numeric programming, or commercial programming. So maybe some of you folks might get into scientific heavy number crunching. So that would be in the numerical programming. System programming, maybe you get into some analytics and stuff like that that you're focusing on, or maybe commercial, a database, and you're trying to make that readily available to users. And so those could have a slightly different set of characteristics that you would find. You want it to be measured easily and widely, have a wide distribution. So these are the things that start to come up to think about it. So the System Performance Evaluation Corporation, or SPEC, they started to make these types of benchmarks that aren't just the how fast the processor goes, what are the megaflops, how many floating point operations per second are processed. And we get into some of those details, like the SPEC CPU 2017. And there's a lot more details about that I'm not going to focus on for time, and it just gets complicated. But this just gives you an idea that stalling goes into a fair amount of depth to give us a perspective of how we're going to answer this question of what is the basis in which, if we do X, Y, Z, how do we know if it actually makes things better or worse? So the SPEC benchmarks are one way of doing that. And this one chart that I showed you about the characteristics for benchmarking gives us a way of getting our head around that. So that's just what I wanted to just give you a sense of. This is another figure that it talks about how they do the evaluation. And so they start, get the next program, run the program 3 times. Guess what? May not actually perform exactly the same. It's going to different parts of memory or other factors that might actually do things. You have to do some selection. And so depending on what that value is and what it means that it would require it to do, it could actually affect the performance. And then is that enough of a decent statistic to come up with a sense of where we want to go or not? And so those are just a few points to be thinking about that. Okay, well, I'll go into the next chapter. Once again, give a context. And so we have these first 2 chapters as an introduction. So we looked at the basic concepts of computing, and we talked about the computer evolution, the IBM 370. We're going to see it a little bit later, the IBM PC, personal computer. They were the first one to come out with that. And then there was a lot of players that came in after that. IBM just decided to, well, recently in the last handful of years, not to be involved with that part of their business that used to be a big workhorse, both in the personal computer and server end. We also talked about performance concepts as we just finished up, and now we're getting into a top level view of computing for function, and think about function and interconnects. So how does a computer actually do execution? There's something called the fetch execute cycle. And when we get into pipelining, we're going to get into even more details of getting a sense of what that is. What are the components? Anybody remember me mentioning something called the von Neumann architecture? Okay, over time, you'll get more familiar with that because I'll be mentioning it. But that's just one of the way of thinking of computer, its basic functions, the CPU, the memory, and the input and output. And Stalling uses a fourth one, the system, the backplane connection. I showed a figure of that last week. Then we're going to be talking about interconnects, and there's a couple of ways of doing it. One that's historical, where it did a point-to-point connection. And anybody ever hear of a parallel port? Some of you geeks, maybe that was like an older style type of connector. Printers used to have parallel ports, and it was literally a point-to-point. You had one wire going to another wire versus a serial, like a USB is a serial connection. And so there isn't a dedicated line for each of these multiple wires. We'll get a chance to look in that in a little bit. And then we'll get into this more flexible area where every computer now is using this PCI or PCIe way of doing interconnections. And so it's a software setup interconnect that's used as long as you need it. And then connection. So here is this term, the von Neumann architecture. It's based on three key concepts. Data instructions are stored in a single read-write memory. So you have the memory. Contents of the memory are addressable by location without regard to the type of data contained there. And the execution occurs in sequential fashion unless explicitly modified. So it's a pipeline. You do one, then you do two, then you do three. Some integrated development environments, they actually have the line numbers, this is the first line, second line. And so it's that you do number one before you do number two, unless you have a branch or some other thing. And interesting enough, we can have this idea, we can program in hardware, we can also program in software. So this is one of the reasons, like the stuff that we're going to be doing with our digital logic design, as well as our Arduino, we're going to actually be programming in hardware. And so thus we have hardware programming, the result of the process of connecting the various components to the desired configuration. So thus you have this things that's all hardwired. You have your soldering iron, if you've ever heard of that. And so you have your data, it goes into the arithmetic and logic functions that are hardwired. And guess what? If it's hardwired, you can't change it. So it's not as flexible, but it can be a lot faster. Or you can be programming in software. So you have the instruction codes. It goes into your general purpose arithmetic and logic functions. An arithmetic logic unit, ALU, is one of the terms I have mentioned and trying to have you guys get familiar with as we go along. So we have what are the main components? We're thinking of this mostly from a software-centric point of view. So it's a sequence of codes or instructions. Part of the hardware interrupts each instruction and generates control signals, provides a new sequence of codes for each new program instead of rewiring the hardware. And then we have the major components. We have the CPU. So it interprets the instructions that are passing its way. And it has a module of general purpose arithmetic and logic functions. So all of that is embedded within the CPU. You have the input and output. And so the inputs, it puts things into the right registers or things for the CPU to do stuff. And then it routes things to the output. All of that is there. And the thing that isn't discussed here is the memory, but that's also another thing that is part of it. We'll have a couple of different acronyms that are used, and I'll try and spell them out more than once, just so you get familiar with the concepts, and maybe over time that you'll get more familiar with the actual acronyms. And so the memory address register, how you keeping track of where you are in memory. The memory buffer register, it contains the data to be written into memory. So that's the stuff that's going to be passed to that location. You have the input and address register. It specifies a particular I/O device. What do you want to do? You want to communicate with the keyboard, the mouse, the screen if you have a touch screen, a peripheral of some sort. And then the I/O buffer register is used for the exchange of data between an I/O module and the CPU. So those just gives you an idea of some of the things that are going on. So at a top level, thinking of the computer components, so we have these three von Neumann areas, the CPU, the memory, and the I/O. And so here we're seeing a little bit of a distinction between where the instructions are located and where the data is. When we start to look at performance, we'll get to that. We can see that the way that memory is accessed for data is different than the way it's done for instructions. Instructions are more sequential. You're not bouncing around as much. Data can be all over the place, but it still can be bound. And so for the I/O, here we can be seeing that we're using buffers to help us to point to different devices. And then we have the CPU with all of these different registers and pointers and stuff like that. We got a chance to mention some of those on the last chart. Okay, we're going to do a pipeline processing capability. This is what we're going to have. It's basically a fetch, execute cycle. Fetch, execute, fetch, execute. You start, and then when you get to the end, then you halt. So that's what a program does. Okay, we're going to be showing some more complexity about this, and then we're going to get into a lot more detail. But at a high level, this is what we do: fetch, execute. And so for this part of this course, introducing this, it's a good place for us to get a place to start. So what is a fetch cycle? The fetch cycle, at the beginning of each instruction cycle, the processor fetches in instructions from memory. The program counter holds the address of the instruction to be fetched. Next, the processor increments the program counter after each instruction fetched, so it will fetch the next instruction in sequence. The fetch instruction is loaded into the instruction register, and the processor interprets the instructions and performs a required action. So we're seeing this kind of thing here. We have a programmable computing environment that we can put things in on an as-needed basis, and it's able to do all kinds of different things and quickly reconfigure to go from one thing to another. So this just gets into a little bit more detail about the various things that are going on. You have the processor memory, the processor I/O, the control, the data processing, all of those things are going on. Now we have the characteristic of a hypothetical machine. Last week, we talked about the IAS, Institute for Advanced Studies. And so here, now we're looking at an instruction and a designation for an integer, and they're both using 16 bits. Okay, now the basis that is common in computers is 64 bits. Eventually, it'll go to 128 bits. It used to be 32 bits. And so thus you have an opcode. And so you wanted to do a store, you wanted to do a read, you wanted to do a jump, something like that. And then you have the address that's associated with this. And this just gives you some high-level perspective of what can go into an instruction and what can be going into the details of one type of way of having some data. So an integer, either positive or negative, you have a sign bit, and then you have the magnitude. All of that is laid out there. So here's an example of a program execution. And so this gets a little bit complicated. So it illustrates a partial program execution showing the relevant portions of memory and processor registers. A program fragment shown adds the contents of the memory word at address 940 to the contents of the memory word at address 941 and stores the result in the latter location. 3 instructions, which can be described as 3 fetch and 3 execute cycles, are required. And so this now just starts to give you an idea of what's going on. You have memory, you have the registers, all of these things are being loaded. And so this is just focusing on the registers and the memory to be thinking about how it works for that. So we have the instruction cycle state diagram. And so we have fetch. Now we have the instruction fetch, the operand fetch. And so remember we had the opcode here. And that would be the operand. And so what are the instructions? And you break it down into components and you start to process it one bit at a time, one portion at a time. Well, anybody ever heard of an interrupt? You guys know what an interrupt is? IRQ. Yeah, I'm more of a computer geek that's got more into software and other things over time. And so that's something that I was familiar with, especially with some of the early programming I did, including assembly language programming. And so you can have different things. The program can cause an interrupt. You can have a timer that it's given so much time to work with the processor, and it says, okay, time's up, you have to go into a pause mode. You can have an interrupt from an IO. Your keyboard, you're trying to press Control-C to make something stop, or there's a hardware failure. These are just examples of the kinds of hardware in terms of categories that you'll be dealing with. So here just gives us an idea of program flow, the program flow of control with and without an interrupt. And so interrupts are provided primarily as a way to improve processing efficiency. So who had ever thought that you interrupt something and do something else, it would make it more efficient? But if it's only taken like 10% of your resources, and you have to wait for that, 5 minutes for this program to finish, you could see that may not be the best way to do that. And so that's what stalling starts to get into, getting into the weeds, going into the kitchen, thinking about processing. So this gives a general idea of transferring the control of to an interrupt. So you have the user program. It says, okay, sorry, tap, tap, you got to stop programming. And then it goes to this interrupt handler and it stores stuff that's being done. It then does this new thing, and then it puts things exactly in the way that it was before it hit the interrupt. That's what's going on. So here we have that fetch execute cycle. We've added a little bit more complexity now, that we can be having an interrupt cycle. So once you've done an execute, you check for an interrupt. And if there's an interrupt, then you take care of that. And then when you're done, you go back to the fetch cycle to your basic program, like we're showing there. This just gets into the program timing, where you would have a short IO wait. So you're doing things and sorry, I got to give some CPU time to something else. And so you're just going to have to pause. It's just trying to illustrate that to give you a perspective of that. Here's an example where there's a longer wait time that you would have to be dealing with and what that would cost. The more typical case, especially for a slow device such as a printer, is that the IO operation will take much more time than executing a sequence of user instructions. And so this figure indicates this case state of affairs. In this case, the user program reaches the second write call before the IO operation spawned by the first call is complete. The result is that the user program is hung up at that point. So you don't want to have things hung waiting for one thing or another. Interrupts is one of the things, and understanding what you're doing with your processing environment can help you to perform better. So now we're seeing the instruction cycle state diagram, but now it includes the interrupts. So we're doing this interrupt handling, and if there's an interrupt, we handle it and then return. So we get some more complexity in a state diagram. Anybody know what a state diagram is? Is that something that you've encountered? Basically, you have like a handful of states in which you're your capability is going to be running. And so is it in a normal operation? Or if you wanted to go more specifically, is it reading in the instruction? Is it, so you can think of a fetch execute, that's two states. Now we get into more states, we're getting into more into the weeds, although those are things that are possible. You can have multiple interrupts, and so we have these different categories of interrupts that we listed here before. See if I can go back to that. Program interrupt, timer interrupt, an IO interrupt, or hardware failure. All of those things are stuff that can be demanding different things going on. And so there also can be priorities of interrupts. A hardware failure, it needs to do something immediately. Probably some of you have heard of the blue screen of death on a Windows machine. Doesn't do it as much as it used to. It used to be quite annoying that they had all of the users be developers in terms of beta testing. Now they've done a better job of testing things before they release them. You can actually have an interrupt of an interrupt. That's also something of what can happen. And so this just gives you an idea of the complexity, what has been thought about over time and built one thing upon another in terms of function. So then we have the input and output function. An IO module can exchange data directly with a processor, okay? And so you can have a PCIe connection directly to the processor that it's not having to go through some intermediaries. And so the processor can read data from or write data to an IO module. So think of your hard drive. You could be thinking of that in an IO module in one way or another. The processor identifies a specific device that is controlled by a particular IO module. The IO instructions rather than memory referencing instructions. In some cases, there's a desire to allow the IO exchange to occur directly with memory. There's something called direct memory access. So if you have slower hardware, if you do this direct memory access, it can try and get rid of some of the intermediaries, and maybe you have some stressed, an older computer, and this can maybe have it still be able to function well. For example, this was a technique that was used that I'm familiar with, that say if you wanted to play a video on a machine and it's a little bit older, if you do this DMA way, it could still render that image and you could still watch that video at a decent rate as compared if it would be doing it in a more, the normal way things flow through the processor. And so that's just an example. So this is just now showing the von Neumann architecture elements of what goes in and what goes out. So that's just a reminder of the von Neumann architecture for that. Okay. Any questions on what I've covered so far? Does that make sense? I know this is, for some of you, maybe most of you, it's the first time you've been exposed to some of these concepts. So some of this is just taking it all in. Well, let me spend some time talking about the inputs and outputs and the various ways of doing that. A data bus, this is going to be more of a point-to-point connection, although there has been moved to doing it more of a PCI, where you have lines that go from one module to another. Could be 32, 64, 128 separate wires that are all put together to form a connection. You need to be thinking about you can have an address bus or a control bus. Those are some ways in which it could be used. This would give you an idea of how it would look. So a motherboard could have some, if you ever looked at a motherboard, it's got like this back plane that all of these things are connected to, and it could be multi-layers of connections. And so we had something look like that that I showed last week when I was showing a microprocessor board. But anyone ever seen a motherboard? Is that something maybe you looked over somebody's shoulders or you played with them? Maybe you're familiar with the idea. I'll show some pictures of that here and there, as well as showing some hardware. Even looking at your Arduino unit, when you get it, when you see this board, you'll see that it has this motherboard kind of look and feel to it. So these are all dedicated point-to-point connections that are in the back plane. So there's good and bad news about point-to-points. This is more of a hardware-centric way of doing an implementation. And they're soldered in, and so they're just going to be like that. They're not going to change. And so that's what you have. So the Stalling talks about the quick path interconnect. So this is something that was introduced back in 2008. You could have multiple direct connections. You could have a layered protocol architecture. You could have packetized data transfer. So a little bit of flexibility that is explored in that regard. This gives you an idea of a multi-core configuration using QPI. So there is some connectivity going among the various cores. Not complete connectivity, but some connectivity. And so it actually has layers. So you mentioned about packets. Anybody ever hear of something called TCP/IP? Some folks may be more into networking. That may be something that you'll bump into. And so there's actually 7 layers here, but for the QPI, there's these layers: the physical layer, the link layer, the routing, and then the protocol. And so it's like you have these different ways of thinking about what's going on based on these layers. This is just another illustration of these point-to-point connections. And so these are the physical interface of an Intel QPI interconnect. So you can see all these wires. And so we're just focusing on this physical layer going between these two elements. So here you have the transmitter lines. So you have one-way directional lines going here, and then one-way directional lines going the other direction. So then the Stalling gets into talking about the other layers. So the link layer, that's the one that's above the physical layer. It performs 2 key functions: flow control and error control. So these are useful things for us to be thinking about what's going on. And so there's these various techniques for doing error control, like here, a cyclical redundancy check. So did something get transmitted correctly or not? And then we have these other 2 layers. A routing layer is used to determine the course that the packet will traverse across the available system interconnects. And it's defined by firmware and describes a possible path that a packet can flow. And finally, you have the protocol layer. So we've worked our way all the way up to the top here for that. It's the packet is defined as a unit of transfer. One key function performed at this level is a cache coherency protocol, which deals with making sure that the main memory values held in multiple caches are consistent. You have all these kind of caches that are there. And this is a way of storing extra stuff, so you don't have to go to further out of your computing environment. And so you want to make sure that they're all having the same information, that it's all in sync. And so that's what we're trying to do with this coherency protocol. And a typical data packet payload is a block of data being sent to or from a cache. So that's kind of a quick synopsis of something that's a little bit older in terms of a protocol. But now we have this peripheral component interconnect. And so it has a dedicated point-to-point connection that then can be released, and that resources can be used for something else. So it's a popular high bandwidth processor, independent bus that can function as a mezzanine or peripheral bus. It delivers better system performance for high-speed I/O systems. There's something called the Special Interest Group. It was created to develop further and maintain the compatibility of the PCI specifications. And you probably have bought various type of peripheral devices. I have an older server at home and I wanted to be hooking up more hard drives to it. And so I bought a PCIe card that could go from a SATA interface to a PCIe. And so it could allow me to hook up more hard drives for my server, because it's basically trying to have more and more data. And so PCIe Express, that's what, or PCIe, it's a point-to-point interconnect scheme intended to replace bus-based schemes such as PCI. So we have PCI, and then we have a more complex way of thinking about that. And the key requirement is high capacity to support the needs of higher data rate I/O devices such as gigabit Ethernet. We had a table last time when we talked about Giganet Ethernet in terms of the input and out devices. And so that's one of the most demanding input and output devices that we'll encounter. Another requirement deals with the need to support time-dependent data streams. And so all of that is possible with what we're considering in this regard. How are we doing? Are you guys still tracking here? I know this gets a little bit complicated, so I'm like taking you guys into the kitchen a little bit, but trying to give you still a top level perspective of what we're trying to explore here. So here it gives us a typical configuration using PCIe. So this figure shows a typical configuration. So there's a root complex device, also referred to as a chipset or a host bridge. It connects the processor and the memory subsystem to the PCIe Express switch. This is what we're seeing here. Fabric comprising one or more PCIe and PCIe switch devices. The root complex acts as a buffering device to deal with differences in data rates in between I/O controller and memory and processor components. So I can have all of these different things, even at different data rates, maybe a legacy component, or just think of your mouse or your keyboard. Then I could have a USB, say a USB-C, that is the latest spec. And so it can actually go faster than a USB 2.0 device or USB 3.0 device. So it's continuing to click up a little bit faster. And so the chipset and going to the processor, I can have all of these different things that are combined, and I can be using what I need at a certain time based on the requirements of what I'm trying to accomplish with my processing. So we had this protocol for the QPI. There was 4 layers. Now for a PCIe, we have 3. We have the physical layer. We had that same thing, so wires to wires connections per se. We have the data link, we have that layer, and then we have a transaction. And so those are the 3 layers that need to be worked out for this type of a connection. So this just gets into more specifics here. PCIe is a point-to-point architecture. Each PCIe port consists of a number of bidirectional lanes. Transfer in each direction in a lane is by means of differential signaling over a pair of wires. A PCIe port can provide 1, 4, 6, 16, or 32 lanes. Those are all possible things that are there. And so you can look in the textbook and read a little bit more about that. So this is trying to give you some insight into the transmit and receive block diagrams for a PCIe. So a common approach and the one used in PCIe 3.0, so that's a protocol based on what Stalling has in this textbook to overcoming the problem of a long string of bits of one's values is scrambling. So this is yet another way of trying to be looking at how to be improving performance. I'm not going to get into that, but I'm just going to mention that there's yet some more complexities that are there. So we have the transaction layer. That's the one that's on top. So sorry, let me. The transaction layer, it receives read and write requests from the software above the TL and creates a request packet for transmission to a destination via the link layer. Most transactions use a split transaction technique. The transaction layer messages and some write transactions are posted transactions, and the transaction packets format support 32-bit memory addressing and extended 64-bit memory addressing. I think I'm going to switch over to talking about some of our project work, and I'll come back to this on Thursday just to finish up our discussion on PCIe. And I could show you some of the devices I have at home. I don't bring all my extra hardware goodies with me, so that'll be something we can think about on Thursday. So I'm going to stop sharing this, and for whatever reason, when I do this in this room, it disconnects me from sharing my screen. So let me share my screen again, and we'll have a little bit of a conversation about our project work. And so how many of you have a good idea of what you want to be doing for your project proposal? Let's have a little bit of a discussion about that, and I'll pull up the what we have here and get a chance to be talking a little bit more about that with you. So what are some of the ideas that you have for your project proposal? Anybody want to throw something out? Nathan, you had an idea that you were talking about. We were talking before class about that. You want to bring that up a little bit?
Yeah, so kind of idea I wanted to use is from experience I've done with my dad. Basically, it's like a security integrator. He's a person that would design and install the security systems at like stores or places that he's I guess contracted to do. And kind of an idea I wanted to come up with is, since we used to work at stores where we had to kind of fix sensormatics, like the sensors that are at the doors, and check the sensors to make sure you're not stealing anything. So kind of idea I was making, or I guess for the whole design was to like create something where the sensor would be detected from those sensormatics.
Yeah. Okay, so Nathan is talking about sensormatics, and maybe you can think of like different types of ways at how you could be protecting a location. I use a simple example, say like you wanted to have your front door, a window, and your garage door. All of those things would be integrated together. And if you get a true that they're in a state of your designation, I would say that that's closed, they're secured, it's going to say that you have a safe configuration. If one of those stops being in that safe, that appropriate configuration, it's going to be flagged, and that would be an example of the security system performing what it's meant to do. Okay, so that could be like an idea of a general concept of what you would be doing for your project. I don't expect everybody to do a project on security systems, but I'm just trying to use that as a point. So that's the first thing. What is a general concept? You want to come up with that general concept, but then you want to start to figure out, well, in your project plan, you're just talking about in a narrative form what you would want to try and do in terms of risk reduction or ways of exploring some of that implementation. So remember last time we talked about the digital logic design? You got everybody, did everybody get that working? Okay, did anybody not get that working on their computer? Okay. We also did the Mars emulator. Did you guys get that working? I also mentioned there's a way that you can be doing it. It's not as good of an interface, but it also is going to be supported longer. You can also do that with VS Code. And I highlighted that there is an instruction for how to do that. And then we have this Arduino. Okay, did everybody order their Arduino kit? Okay, please order your kit right away. Order it now because you're going to need it. And I don't want it to be that you're late or not able to submit your Arduino part of your project when it becomes required. So in terms of your proposal, let's break this down. I'm going to use Nathan's example since it's related to what I was speaking about. So your digital logic design, you can actually be programming in hardware. So guess what? You guys have programmed in software, but now you're going to get a chance to program in hardware. This is something that's been done for a long time, not with AND gates and OR gates and inverters, which we're going to get a better chance to know what that means. So I could have anybody have an idea with my example, if you wanted to secure a garage door, a window, and your front door, how would you aggregate that together to have it come up with a true state if they're all secure? Anybody have an idea how you would do that in digital logic? We have a couple engineers, mostly computer science folks. Go ahead.
So the true state they're all secure?
Yeah. Yeah, right. So we would be using 2 AND gates. And I mentioned that briefly on Thursday to give you an example. So that can be one of the 3 digital logic circuits that you would create. Nathan mentioned like another type of way that you could be having for a surveillance system, a home protection system, is you have a motion detector. Okay, well, we don't have a motion detector. In your Arduino kit, you will have a light sensor, so you could probably mimic that a little bit. And there's also a thermal sensor, thermocouple. So maybe instead of just these 3 inputs, you have that same circuit, you copy it, and then you start adding another additional electronic to that, making it more robust. And I'll show you some examples of that on Thursday of some things that I did trying to program in hardware some things on that in that regard. So you guys understand the general concept of what I'm mentioning that? So for your proposal, you're just mentioning I'm going to program with digital electronics the capability for a home security system using Nathan's idea. Next, we have the assembly language. And so this one may be a little bit more complicated to tie it into the theme, so give it a go. And the thing where this starts to play out is you're going to be communicating directly with the registers, input and outputs to the CPU, a Mars MIPS processor. The MIPS processor is what we'll get into, and I'm going to talk a little bit more about that as we go along in our course. So I think most, if not everybody, has never programmed in assembly language. So just started out something with doing a hello world. I just briefly showed you that on Thursday. I will go over that in more detail. That could be a first thing of just how you could take a message that's stored in a register and have it print out to your console. First step. How are you going to start to engage with this processor or this microcontroller? That's another word I'm going to talk about. Sometimes a simpler processor is actually called a microcontroller. And then you could say, instead of saying hello world, how about hello APU students in CS 360 or something like that. And maybe you could start to do some more manipulation. And I'll be showing you some examples of assembly language programs to give you some perspective on that. And finally, you get into the Arduino unit where you do these cyber physical designs, now you could start to be going back to what you did up here, where you can actually have some real push buttons. Say you're trying to emulate a door, a window, and a garage door, and you could have it tied to an LED that either turns on or off based on if it's true or false. So you can be thinking about, once again, the context is programming. Some of this is a higher level abstraction. You're trying to get the essence of what it's supposed to be doing in terms of its functionality. We encountered this one concept, a state machine diagram. So what are the various states it's going to be in? Either a secure state or a state that's indicating that something is not secure. So you could say that there's two states at a high level for that security example. So that's what you're going to be putting in your proposal. What's the general idea? Come up with a title, an introduction, and what would you like to explore as you're thinking at this point of the course that you would like to develop in each of these three areas. Does that make sense? Do you guys follow what I said? For those online, Freddie and Bahrain, does that make sense? You guys tracking that? Okay, thank you, Freddie. And Bahrain, you can just let me know if you have any questions. So that's just a general sense of what we're doing at this level in our development of our project. So like I said, Thursday will be more of our hands-on day. I'm going to be slowly introducing some software and some hardware concepts. I'll show you some of my goodie drawer of things that I could be sharing with you about electronics and stuff like that. So I think that will be fun. Also, it's a chance for us to be sharing some of the stuff that you're developing over time. Keep asking questions, send me an email. That's probably the best way to reach out. And we could set up a time to talk in more detail if there's something that you still think that you need a little bit more clarification on. Any other comments or questions that people have? It's actually a fun course. I love teaching it, and I love a lot of the things that we get a chance to get exposed to. It can get a little bit complicated at times, but I'm trying to keep it at a high enough context that I don't lose all of you guys. And so that's an important thing for me. Go ahead, Nathan.
I forgot to mention, is there a certain amount of paper you need to write for the project proposal?
I do have a rubric here, and so you can be looking over that. It's not too complicated here. The depth of proposal, so it's trying to be more of looking at, does it adequately cover what you're trying to say? So you need, for an introduction, at least a paragraph for each one of these. So 4 to 5 paragraphs or something like that would be what I'm looking for. Okay.
Wait, if it's 4 or 5 there, you want to try like a conclusion?
Yeah. So an introduction, what a good way of writing is have an introduction, the body, and a conclusion. So remember that what you have, you have your project proposal, then you're going to have these 3 specific things that are going to go into detail for each one of those 3 areas. And then you're going to have a final report. So what kind of things are you hoping will be outcomes that you could be referring to, and that you've done this in your final report? So it's like a proposal, like you wanted to have someone to pay you to do some of this development work and demonstrate for this new application that you see as high risk. We were able to reduce that risk and actually have a demonstration of this. And so we think this is a promising technology, blah, 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 blah. Those are the kind of things that I'm trying to do with this flow with the way we lay it out. Okay, Victor?
Well, otherwise, we've been working in a micro
Uh-huh.
very similar to a project for this course.
Yeah.
I think it's a good project.
Well, you can leverage that definitely for sure, but I'd like to see how you could maybe, maybe extended it a little bit more, but what that means for you, Victor, instead of starting from 0, you're starting from
Some,
a little bit higher. And so what are the things that you want to try and demonstrate that? What are your research questions?
for like a competition.
Yeah,
We have a base, and then
yeah,
the microbus is supposed to be so.
yeah.
That's
Mhm.
that's one, and then basically what we want to get is speed from that, like whoever
Mhm.
is faster, the better.
Yeah, so,
We have to use less,
okay,
that's very-
yeah. I think you can definitely use that. So you got your speed of, just say 30 seconds.
Yeah.
Could I get it down to 25? Does it need more sensors? Does it need a faster actuator? What are some things that you could be thinking about? Is a programming, it's sensing where it is? Does it need to be written in assembly language to make it faster? Those are just like examples off the top of my head, how you're trying to talk about, this module navigating through a maze. And so just like we're talking about processor architectures, Stalling mentioned is trying to improve performance. What could you do to make it actually do better?
And one last question. The micromouse, I did not use specific assembly language, but it's like a language based on assembly.
Yeah.
That is still be fine.
I'd like you to use the assembly language. And so maybe that's the one thing that you would have to take some of those ideas and figure if you had a MIPS-based processor, how would you improve performance using that type of a processor? Okay? Any other comments or questions? It can also be a lot of fun getting a chance to see what everybody's doing, and students can see what other students have been coming up with some cool ideas. So that'll be great. All right, well, I think that's a good breaking point. I'll stop the recording there, and I'll look forward to seeing you all on Thursday. Take care.